Okay, let's start. Comments on the quiz, just so that everyone actually understands how it was graded. So this is the second quiz you're seeing, so you kind of know the format already. But in general, quizzes are going to be graded such that each response is worth the same amount, so there's no point in getting stuck on something. You always try to do as much as you can. So 1 point for each correct response. And so, also someone reminded me that I actually didn't show you guys how to sketch inequalities, even though I thought I did, before this quiz. So this was moved down to the bonus. So technically, this quiz is out of 1, 2, 3, 4, 5, 6 points. So 6 is the maximum. Now, as is typical, what I'll do is I'll also give you guys bonus problems on quizzes where those have to deal with the next section. It's purposefully on things that I have not yet taught to see who's reading ahead or just to give you a shot at doing better. So anything you got above 6 will count extra. And how I deal with those extra points is that I'll just collect them. And then at the end of the semester, like the quizzes where you might have gotten less than 100 on, I'll redistribute the points there, right? So it's kind of like extra credit is built in. So I'm not giving anyone extra credit here. The bonus is your extra credit. You want extra credit, read ahead a little bit and try to get the extra problems done. Yeah, so that's how that works. So the maximum here was 6. Most people actually got, I wouldn't say most, like 60% of the class around there actually got more than 100. So yeah, so that means several things. You guys have a cushion for the next graded quiz, so you can actually like get 4 problems wrong on purpose, or why would you do that, but whatever, technically you could, and it will still like count as 100 because I'll take these extra points and move over there. It also probably means my quizzes are too easy, so I should make them harder. Yeah, that's definitely, yeah, way too easy. So, yeah, so just to make sure that you understand how the grades work. So if you got something higher than 6, that all those extra points count to extra. So you would have like 2 grades, so it would be like 5, there's a circle plus a 3, and you'd write down 8. What that means is you got 5 points in the actual quiz, 3 points from bonus problems, and so the total is 8, but technically the maximum was 6, so that's how you want to think about it. And in your report cards, I'll actually mention that. So on your report cards, if you have something bigger than 6, what I will do is I will enter a grade of 6, and then I'll make a note that says, oh, you have 2 extra points saved up for some future date. So I'll actually type out a note beside the grade. So that's how that's going to work. Just want to make sure everyone understands that situation. And with that, we are simply going to move on. We finished talking about PEMDAS last time. Got a little bit heated, but we made it through. Now we're going to move on to, again, some hopefully familiar things, which it seems familiar because the bonus points problems were a lot about what I'm about to talk about, and a lot of people actually got them. So we are going to, I forgot what section, I think it's 1.2 or 1.3. We're going to talk about exponents. Or the laws of exponents, or exponents and radicals would actually fall under here. So let's actually just jump into it. Assuming n is a non-negative integer. Right, so we mentioned what integers were. These were just whole numbers. Non-negative means it's not negative, it's positive, it's 0 or bigger. We write a to the n to mean a times a multiplied by itself n times. Right? So here n is called the exponent, or power. A is called the base. a to the n is an exponential expression. Okay. So that's the basic idea. If you raise something to like the second power or the third power, what that means is you're taking that thing, you're multiplying it by itself 2 or 3 times, as is indicated. Now, that's the basic idea, but of course, math people found out a way to generalize this. This can be generalized to other kinds of numbers. This leads to. So we came up with a bunch of rules that kind of maintained this spirit, but allowed us to use more exotic numbers. So these rules allow us to work with numbers that are not non-negative integers, but at the same time it'll always maintain the rules that we expect from this basic definition. And we call these rules the laws of exponents. So I will simply list them. These are things now that you have to have memorized. I'm just going to list them, maybe explain a little bit. So here's one rule. If you have 2 exponential expressions multiplying each other, what happens?
You add them.
You add the exponents, you add the powers. Okay? And why? That's because this is really a list of a x's and this is really a list of b x's, and so in total you have a plus b x's, right? So that happens there. Similarly, if you have this situation, this is x of a minus b, because on the top you'll have a list of a x's, on the bottom you have a list of b x's, and you can start canceling them, and you're always going to be left over with a minus b x's left over. This, of course, leads to the idea of what if you subtracted something and you would have a negative, right? So what if the number a is smaller than the number b? You'll get a negative. So we have the rule for this, which is going to be what? 1 over x to the a, right? Because if there are more b's than there are a's, everyone in the top is going to get cancels and leaves you over with some people in the bottom. Hence, this makes sense. And of course, for here, x cannot be 0 because we can't divide by 0. And here, of course, also x, you assume that we can't be 0 when we're doing something like that. We have some other rules. For example, if we have x to the 1, what is that? Well, that's just x based on strictly from the definition. What if we have x to the 0? This is 1. This is assuming x is not equal to 0. If you want to see why x to the 0 equals 1, what you have to do is go to the previous rule here. Set a equals to b, that gives you x to the 0 over here. But if a equals b over here, everyone cancels and gives you 1. So you get x equals x to the 0 equals 1. Right? So like I said, these rules maintain all the previous definitions, so they're not random completely. They do want to maintain an idea. Another thing we can learn about exponents is that they do distribute across products and division. So if I have x times y all to the a, that is the same as x to the a, y to the a. So that's true. And if you want to see why that is true, well, if you have a copies of x, y, you can rearrange them to group all the x's together and rearrange to group all the y's to the other side, and you have a copies of x and a copies of y. Right? So it makes sense that powers distribute across products. They also will distribute across divisions for the same reason. If you have a copies of x, y, using the rules that I told you how to multiply fractions, you'll just multiply all the x's across the top, you'll have a of them. You multiply all the y's across the bottom, you'll have a of those. And so you would end up with that. So it makes sense for powers to distribute across divisions. Now, there is another one, and this is the rule that kind of leads into radicals. It's when we have x to the something like a over b. So when you have a fraction in the power. And this is the one that a few people got wrong on the quiz. This was one of the bonus points. Some people got it correct, but this is the one that stumped a few people. I asked about those over there, and most people knew those. This one, what is this one?
Square root of b. Square root of b. Or like the root of b.
Well, the bth root is what we call it, of x to the a. So you end up with this symbol here called a radical. And this is actually equal to the b root of x raised to the a. And these are interchangeable as long as your x is not negative. If your x is negative, there are some issues that can arise, and I'll deal with those later on. Interchangeable. If x is greater than or equal to 0. So we have those rules. Now, if you don't know that, or you happen to be the person who forgets that sometime, there is a way to actually remember that. It's called flower power. You know, even myself as a grown man, I still use this in my head sometimes. It's really embarrassing. But when you have a power here, you kind of imagine a flower, right? And in a flower, this is like the division sign. The bottom is the root, right, which is another name for radical, and the top is of course the flower, which rhymes with power, hence the name flower power. So the top is always going to be the power, and the bottom is always going to be the root. So the bottom number always goes on the radical, the top number will go on the x itself, or you can put it slightly outside the x as long as your x is positive. And it is worth mentioning that one would usually be easier to compute than the other. It tends to be easier to take the radical first. Another way to actually see it, and then I'll talk about that. Is because of another rule that I forgot to mention. Is that you multiply powers in this case, right? So it's like you have b copies of x to the a. If you add up all the x's, you'll have a times b. And so this would mean if you have x to the a over b, you can often think of it as x to the a, and you can factor off a 1 over b. And so the power is on the a, or whenever you have this division here, it means to actually take the radical. And when we talk about solving equations, that's going to be clear. Why would 1 over b mean radical? What does radical even mean? We'll get to that. But that's another rule. You should also be aware, one can be easier to compute than the other. Usually the radical is going to be the one that's easier to deal with first. So if I have, say, 9 to the 3 halves, now I can think of that as the radical of 9 cubed, or I can think of that as the radical of 9 cubed. Now, for this one, following PEMDAS, you'd have to actually find 9 cubed first, and who's going to remember that? Then you're going to have to square root that. It's going to be a big number. But if I think of it in this way, the radical of 9 is just 3. And then I have to compute 3 cubed, and the answer is 27. It's much easier to compute in my head. So this one is going to be easier. So you can interchange them. Just make sure that the thing that's inside the radical is a positive number or 0. And you can interchange them at will, and you just go with whichever one is easier to compute. So most people are familiar with those, so I don't think I wrote down too many examples. So let's talk about radicals. We're going to get to some examples at the end. Right now, these are just the rules. I want you to have them memorized. So there are 9 rules of exponents that you should know very well, and you should be able to apply in various contexts. talk about radicals. So, a radical is an exponential expression with a non-integer fraction exponent. That's all it is. So for example, if you see like x to the 1/2 or x to the 1/3 or x to the 1/7, anything of that sort, these are called radicals. So there's something called a principal radical. You don't really need to know the name, but I'm just going to tell you just to be precise. And that just means these are things that have the form x to the 1 over n. Right? So when the numerator is 1, we call it a principal radical. But we may think of radicals more generally. So x to the 2/3, you might think of it as a radical expression. X to the -5 over 4, you might think of it as a radical expression, etc. These are all going to be thought to us of radicals. Now, I want to mention the domain of the radical. And this is basically saying when radicals work. And it depends on the actual number that's involved. So if we look at the domain of something that looks like x to the n, there are 2 rules to tell you where it will work. So the domain of that is going to actually be all non-negative real numbers. So this means that x must be in this set. So this tells you x is a member of this set for that expression to work. This is 1 over n. And this is in the case where n is even. So that's like x to the 1/2, x to the 1/4, x to the 1/6, x to the 1 over 1,228, whatever. As long as the n is even, what you're plugging into this function can only be positive. And it'll actually, everything will work because n is odd. So, and we actually spoke about this last time, but I just want to actually write it down specifically. So, example, for x to the 1/2, or x to the 1 over 16, or x to the 1 over 12, etc. Your x must be greater than or equal to 0. Whereas for say like x to the 1/3 or x to the 1/9, etc., x can be any real number. So far, I don't think I've said anything too crazy. Just making sure that we're all on the same page here. What next there was? We'll get to some examples pretty soon. Don't worry. Now let's talk about the meaning, and then let's talk about some properties, and then we can get to examples. So let's get to this one. So meaning. What does it actually mean to take a radical? To say that, and by the way, I didn't actually say what we might call this. This is called the nth root of x, and if n equals 2, we call it the square root of x. And we write, you don't actually write the 2, you just don't write anything. If n equals 3, what do we call it if n equals 3? This is called the cube root of x. And that would look like that. That's called cube root, square root, cube root. But in general, you'd say the nth root. So if this number is a 5, you say the 5th root of x. If the number is a 17, it's the 17th root of x. But what does it mean to say something is the 17th root of something else? Well, to say that this is equal to y is the same as saying that if I take y to the nth power, I would get x. Right? So that's going to be the meaning behind what that symbol means. And so the idea is, if I have a situation like this, so let me write this down. We'll be using this more regularly. The idea here is if we're given something like y to the n equals x, and we want to solve for y, what we can do is we can take that equation, and I'm actually going to talk about equations more generally soon, and this symbol means that both sides give you the same thing. So if you want to manipulate this equation, you have to manipulate both sides in exactly the same way. And so we can take advantage of the laws of exponents. To solve for y's to make it y to the 1. We have a rule that says y equals y to the 1. So what that means is if I have y to the n and I want to obtain y to the 1, what I can do is I can raise this to a power that's going to make multiplying that n become 1. And 1 over n is going to be the guy that does that. The laws of fractions that we looked at. Right? So by doing this process here, this can simplify to just y to the 1, which is what we want. And because it's an equation, I would have to do this over here as well. So I end up with this thing. So a radical is just something that naturally arises by us being able to solve equations for certain things. If we want to undo a power, a radical is the way we're going to do it. And again, this can work more generally. So if you have like y to the a over b equals x, and you want to solve for y, you can actually raise this to the b over a. And so you have to raise that side to the b over a. And that will allow you to solve for the y. This gives you a more general kind of radical. But that's kind of the idea. This is what a radical means. It's kind of like the inverse of the exponentiation rule, right? If you want to undo an exponential, like someone multiplies something by itself a bunch of times and you want to find back the original guy that they multiplied by, you want to go back to the beginning, you use a radical. That's the idea. So when I say, I guess I know you all know this, but just to be clear, so if I say the square root of 16, right, so this is called the square root of 16, what this means is, what number did I square to get 16 in the first place? Right? And the answer to that is of course going to be 4. So we can say the square root of 16 is 4. Because what did I have to multiply by itself twice in order to get the number 16? 4 was the answer to that question. And so that's what a radical means. And so you can always think of it as just like reversing exponentiation, and using the log and using the exponential rules, we can actually manipulate these expressions. We're going to have a lot of practice where we're doing that. Before that, I want to write down some properties of radicals. Now, just remember a radical is an exponent, so they have similar properties. And let's look at some properties of radicals. But if you know the properties of exponents, you'll automatically know these as well. So, for example, radicals will also distribute across products because powers distribute across products. So if you have the radical of a product, you can split it into a product of radicals. If you have a division, a radical of a division, you can split the radical across the division. That's legal. And of course your E is not 0 here. If you take a radical of something that's already radicalized, so if you have a radical, you have something with a radical, and you took another radical, that's perfectly fine. The radical becomes the multiplication. And if you look at this as laws of exponents, that makes total sense, because this just means you have a to the 1 over n, and then you take that to the 1 over m. The rules of exponents tell us we multiply these. So that just means that. So that follows directly from the rules. And this is more of a neato fact. We spoke about absolute values last time. So here's something that you should be aware of. It'll help you out, especially in calculus every now and then. 4. If you look at the nth root of a to the n, it turns out that it could be one of two things. Now if you raise a to the nth power and then take the nth root, what is the result of that operation? Now a lot of people might just say, well, you just raised something to a power and then you undid that, so you should get a. But that is not actually true. You only get a if n is odd. And you will get, in general, you will get the absolute value of a if n is even. And now, you can actually think about that. If I take a negative number and I square it, I get a positive number, then I take the square root. I started with a negative number, but the result was a positive number. So if n is even, the result is always going to be positive. That's just another way of saying absolute value of a. So, for example, the square root of x squared is equal to the absolute value of x. And in fact, this is sometimes used as an alternative definition. When someone says, what is that? This is one possible answer that you can say. The definition I gave you before, though, I think is much better. It's much more applicable to many more situations. But I think knowing that absolute value is, it's x if x is positive, it's 0 if x is 0, and it's negative x if x is negative, that's a much better way to think about the absolute value. But this is actually equivalent to that. This function will output all the same outputs as this function. And this goes for like the 4th root of x to the 4th, the 6th root of x to the 6th, etc. You don't actually get x back, you get the absolute value of x. In the case that it's like a cube root of x cubed, you get exactly x back. If you started with a negative, you'll end up with a negative, etc. Okay. Some of you are probably bored. Let's actually get to some problems here to make sure that we understand how these guys actually work and that we can manipulate them. And while we're going through these, I'll give you some recommendations for how you want to actually approach such problems. So, for the following, I want you to simplify and combine. A. by simplifying here, I mean, we call the phrase rationalize. We're going to need to be able to simplify expressions like that or worse. Let's give you some time to copy those down. Let's actually do these together. Let's start with the first one. Okay, so for A, this is equal to, what do you want to do here? Distribute what?
The exponents to each one.
Exponents, we have a rule that says x to the a raised to the b is equal to x to the a times b. So that's probably the first thing I would do. Again, that's kind of indicated by PEMDAS. We have things here being raised to exponents. We have a division, and then we have something else raised to exponents. PEMDAS says we deal with the exponents first, and then worry about the division. So that's what we're going to do. So we're going to go m and simplify this. It's going to be m to the, do I have to write 6 times minus 2? I don't know. Is that safe? Okay. If you don't feel safe with anything I write down and you're not sure, ask me. I'll write down the extra steps. But I'm going to assume that we all know where that 12 came from. Okay. Now here, we're going to have m to the 3 times 4. It's also 12. Now down here, we're going to have m to the minus 15. Now, the next step is, well, we have a multiplication here, right? So here you're going to add the exponents. You're going to get m to the 0, because minus 12. Right? Now m to the 0 is of course 1, so we have 1 over m to the minus 15. Now, we can simplify that a little bit to, let's say if I wanted to get rid of the negative power, what is that? Right, it's just m to the positive 15, right? And the reason why, and see why, that's because this is m to the minus 15. You can think of it as 1 over m to the 15. And then this is just one fraction divided by another fraction. So you keep change flip, you get m to the 15. So that is the simplest form that we can write that into. So that's just a very complicated way of writing m to the 15. So in B, we have a radical involved. That's a fourth radical. It's a to the 16, b to the 8th, c to the minus 12. Now we're told that the a, b, c are non-negative. Now why that's important, just so I want you to be aware of this. I don't want it to be lost on you what's going on here. What this means is that you don't need to worry about the absolute values. Now, it's very important that you have whenever you see some sort of mathematical expression, one of the first things you're going to want to be thinking about is, does it actually make sense to write this expression down in the first place? Like, if you see a fourth root, you should automatically start worrying about, well, what if one of these are negative, right? That should automatically be a worry to you, because you know the fourth root is not going to work if they're negative, okay? So me telling you this is telling you, oh, you don't need to worry about that case. It wasn't just something that's written there for no reason. The problem, how you deal with a problem, will be very different if this was not given, right? And I might show you how it's different soon, but it's actually this piece of information here is actually important. Telling you that everything is positive, the absolute value is always going to return the same number as the original. Okay, so it's not something to be ignored. Why? Because, for example, let me just quickly give you the example here. Like if I said, okay, what is the fourth root of a to the 12th? Now, if I just ask you that, the correct answer is going to be the absolute value of a cubed. Okay? Now, if I told you this, and a is greater than or equal to 0, then that you would simply write a cubed. Now, had I not told you that, and you wrote a cubed, the answer would be incorrect, because you would need the absolute value. This is actually important. So if I told you the fourth root of a to the 12th, and you write down a cubed, this is actually incorrect in general. So that's actually important. Okay, so just be aware of that. Sometimes I know you're in a textbook and you just read a problem and you see them make a little statement to the side over here, and you kind of just ignore it and do the problem anyway because I'm just applying these rules. And you never actually think about what you're doing. But yeah, math people tend not to write something down unless it's important. So if they express that, there is a reason for expressing it. Okay, and the reason is you don't have to worry about absolute values. Whereas, if it was not expressed, you'd have to worry about absolute values. Okay. So, me saying that says you don't have to worry about absolute values, just kind of apply the rules directly as you saw me list them in the previous section. Okay, let's go. What do we do here? You can separate them. There's a rule that says I can just deal with each of these individually, because radicals distribute across products. Now, remember what this expression actually means. It really means, and you don't necessarily have to write this down if you already see it, this really means a to the 16 raised to the 1/4. This really means b to the 8th raised to the 1/4. And this really means c to the minus 12 raised to the 1/4. But ultimately, if you just see, you can just literally divide this 4 into the 16. So 4 into 16 goes 4 times. which is equivalent to taking 16 times 1 over 4. And so similarly here, we're going to get b squared. And similarly here, we're going to get c to the minus 3. Which is equal to, if I don't want negative powers, a to the 4th b squared over c cubed. And at this point, I can also mention something. A lot of times in pre-calc and algebra class, your math teachers tend to make you think that there's something bad about having negative powers. Like, no negative powers in your answer. You're just negative, move it in the bottom, right? And they're like, oh, you have to write your answer like this or it's wrong. Calculus and above, no one cares, right? Or if they're saying, oh, you can't have a radical in the denominator, you have to rationalize. Calculus and above, no one cares. Like, there's no such thing as an ugly number, really. The point of us asking you to manipulate things so that there are no negative powers is just, it's an extra step to tell us that you actually know how the rules are working. It's just extra practice, right? But there's nothing wrong with writing this as the answer in general, okay? The instructions on a problem might say something like, make sure there are no negative powers in your answer. Now, if that is not there, I don't care, okay? Just so we're clear, that it's not, one is not more right than the other. I find a lot of students are confused by that. You know, I tell them, like, this is the answer. No, my professor would mark that wrong. Like, that's the answer. No, you have to write it like this. Okay, fine. But in general, there's nothing wrong with either one. So, unless instructions specifically tell you to write it in that form, you don't need to. Any questions on this? You have all these kids with these math triggers, you know, if I write that down, they start rocking and they're I don't know, but I'm not really comfortable with this going on. Like, Jesus. It's okay, really. It doesn't matter as much as you think it does. Yeah, 48, x to the 4th, y to the 5th. Now, I'm going to say something about this one that might seem a little bit weird. So here's something. What I notice students like to do whenever they see an expression like this, a lot of them like to kind of be using the negative as a flipping cue. So they're saying, oh, a negative here means I flip this upside down, and a negative here means I can swap this guy to the top. And what normally happens is, like, if this is repeated, like if you have x to the negative 3, y cubed, z to the minus 1, and then you over here you have x squared, and you have y to the minus 5, you have z to the minus 2. What I've seen happen a lot is students start switching things up and down, and like they're doing this with multiple things, and they usually mess up somewhere. Like I would recommend that don't really just start flipping a bunch of things all at once. You don't want to do that. And again, not that it's wrong, but statistically speaking, the students who do that a lot tend to get problems wrong, because they forget to switch one of them or something like that. So that's just a general recommendation. So don't really think of the negative as a flipping thing, at least not in the beginning. It's much better to actually think of things this way. It's going to be a lot nicer to think of things this way. So first, I would think of PEMDAS. Now PEMDAS says, do what's in the parentheses first. So don't worry about flipping things over to the 5th yet. Worry about what's in the parentheses first. Now the easiest way to worry about what's in the parentheses that I have found that causes the least amount of mistakes is to actually separate the like terms, separate the guys inside. So you're going to think of it as, just think of the constants separately from the x's, separately from the y's. Right, so you kind of dissect them. In your mind maybe, but if not, and if there's a lot of stuff and it looks complicated, literally write out a step where you're separating things. I'll keep the numbers together, keep the x's together, keep the y's together, and you just deal with it that way, right? It's less room for error here. And again, it's not wrong to do something other than this, but this is really a recommended step here. People tend to not make silly mistakes if they think of it this way, because everything is neatly compartmentalized, and they can just think about one thing at a time and just go through without. But then if they think of it like, oh, I'm flipping 5 things at a time. Now your brain has to keep up with 5 operations instead of just 1 operation at a time. And when you're anxious and you're on a test and you're rushing, you don't want to give your brain too much things to do. Remember, it's in saber-toothed tiger mode, right? You want to keep instructions very simple, 1 thing at a time. Okay. So the first thing I'm going to do is start to simplify these. So what is the 48 over 24? 2. That's just simplifies to 2. X to the 4th over x to the 1?
X cubed.
Right. And again, that's x cubed, and that's because it's the 4 minus the 1. I'm applying that rule. Y to the 5th over y to the minus 2?
Y to the 7th.
Y to the 7th. And I'm not thinking of flipping. I'm literally thinking of the rule where I subtract the powers. Right? I'm literally thinking here 5 minus a minus 2. Right? So I'm not thinking of swapping a place. I'm thinking of applying a rule. There are these 9 rules that I have memorized, and I know them extremely well. Every step I take, there's going to be a rule I'm thinking of that tells me to take it. That, by the way, is a good principle in general for mathematics. Do not write down anything unless there's a rule that you specifically think of that is correct, that tells you that it's okay to do that thing. Right? When students get in trouble when they start to guess, they start to do what feels like it's going to get them out of trouble. You know, like they'll see like a radical of 3x y to the 4th, and I tell them to simplify it, and then what they do is like, they just square it. Why? To get rid of the radical. For no reason, they just square it. And I'm like, that's wrong. Why would you square it? Right? Like if I told you I'm going to give you owe me $1,000, would you randomly just square it? Oh, now you want to pay me $1 million? No, you wouldn't do that. What was the reason for the square? There was no reason. You felt uncomfortable because of the radical, and you just wanted to get rid of it. You didn't think of a rule, you panicked, right? The proper way to study mathematics is you learn the rules very well, so familiar that you can see them as templates. Every single line you write down, there's a rule that you were thinking of, why you wrote it down. I did not write that down because I panicked. I wrote it down because that was rule number 5 in this section, right? Now, to be fair, at first, it's going to take you a longer time to do problems. Like okay, now I have to look up a rule to know what I can do. Okay, I can do that. And it'll take a while, but eventually you get used to it. Eventually you'll start to memorize the rules. You start to see it, you'll do it automatically. But that's where you want to start. You don't want to do anything because of panic. There's a specific rule I'm thinking of. I didn't have a rule that says, oh, you can swap out things. No, I have a rule that says, if there's a division occurring, I can subtract the powers. If there's a multiplication occurring, I can add the powers. These are the rules. Every step you take, there must be a rule in mind for taking that. Now, here, what was the rule that we had when we had a multiplication and a power?
Each one gets the power.
Each one gets the power, right? So I'm not thinking about, oh, flip this upside down. Like, no, I'm going to go slowly and attach this power to each person. And now I have that. And now, after everything is simplified as much as is possible, there are no parentheses or any divisions or any weird signs, now I can think about applying some other rule if I want to. Now I can move this down. Now I can move that down. Now I can move that down. Or if you want, this is going to be 1 over 32 x to the 15. Really practice making steps based on some established rule. Do not do anything because you panic. Do not do anything. Do not randomly square something because you know it will get rid of a radical. There's always a specific reason, right? Like to go back to this random squaring example that I just gave you, right? If I told you simplify that, it's not okay to just randomly square. If there's an equal 4, now it's okay to square, right? But you have to square both sides, right? So there are certain times when the situation can tell you what can be done, but in all cases, there has to be a rule that says it's okay. There is no rule that says you can randomly square an expression. There is a rule that says you can square both sides of an equation, which means there must be an equal sign present before you go around squaring stuff, right? If there's no equal sign there, you can't randomly square. Equal sign, now I can. Why? The rules say so, right? And if you want to get too philosophical, remember what I told you. These are just rules to a game, like the rules of chess. The knight moves in an L. Why? It doesn't matter. That's how it moves. That's the rule. If you move the knight in any other shape other than an L, you're not playing chess anymore. You're doing something else and you're going to mess up. So that's pretty much where I take that one. Now, the next example is pretty much just a warm-up for the following example after this. Okay, simplify that. So simplify and combine is going to be the idea. Does anyone know how we would deal with situations like this? Yeah, Aaron?
Find the radical, like, so for 20 would be like 5 radical 4, and then, I mean, that's how I did it, and then from there.
Right, so you would rewrite the expression, because the square root of 20, I don't really know what that is. You want to rewrite the expressions into factors or products where you actually know the radical of something in there. So the 20 I would think of as 4 times 5. I know the radical of 4, the radical of 5 is the weird one, but now I can actually break it down a little simpler. 80.
40 and 20. 40 and 2.
16 and 5.
16 and 5 is a nice one. Now, by the way, you could break this down in steps. So for the 80, you could take a step and go, okay, well, it's 4 times 20. But then you'd realize, oh, I can break down the 20 into a 4 times a 5. Right? So if you take an extra step, there's no problem with that, especially if you're doing it quickly. And so eventually you'll get to the 16 times 5. But this is how you're going to start to think. So if there's something under a radical and it's kind of weird, start thinking of breaking it into products. Where you know how to take the radical of some of the products, and you might not know how to take the radical of some of the factors, you might not know how to take the radical of the others. This one?
9.
Right, 9 times 5. Now we start to see a pattern. 5 happens to be the weird guy that's left over all the time. So, and this step is going to be more important in future sections, but at this point, people usually don't write this next line I'm about to write down. You are going to think of splitting it like this. And to make things a little bit safer, I want you to notice that, again, that's not something random. I'm splitting it with a certain pattern. Under the first radical, I put what can simplify. Under the second radical, I put what I can simplify. I can simplify radical 4. I can't simplify radical 5. There's a nice number that I know of that actually does this. There isn't a nice number that I know of that does that. And of course, all numbers are nice. You know what I mean. Right? I can simplify radical 16. I can't simplify radical 5. I can simplify radical 9. I can't simplify radical 5. So that should be kind of how you're thinking about it. But from this step, people usually jump to the following step. Simplify the radical 4, leave the radical 5, minus 16 is 4, leave the radical 5, plus radical 9 is 3, leave the radical 5. So that all becomes that. I simplify the guys in the front. And now, what can I do here?
From left to right, add them as a correct one.
Yeah, add them, right? Here you'll notice that there's a common element in all of these. This is called the GCF, or in this situation, you would say that these guys are like terms, and we can add like terms. So it's like 2 apples minus 4 apples plus 3 apples, or that kind of thing. Okay, so we have 2 of this thing minus 4 of that thing plus 3 of that thing. At the end of the day, we have, right, we have 1 of that thing, right? So we have 5 of them minus 4 of them. We're left over with 1 of them. And that expression simplifies to radical 5. Now, apply that same idea to the next one. And remember, I said they were all positive here, and again, that's because I don't want you to worry about the absolute values at this moment. Okay, take 2 minutes and try that one. Or you already tried it, you can tell me what you did. Did anyone actually do this one already? Okay. How did you actually do it? Or what was your final answer?
Oh wait, I actually skipped one. Oh wait, no, I didn't. I got 14b radical 5, a to the 5, c to the
A to the 5, C to the 3? Like this?
yeah.
That's the final answer?
That's what I got.
Is that what you got? Did anyone else try this one? Well, let's see. Let's see how would we do this. So, again, there's going to be the similar idea of we wanting to split up the radical into things that we can simplify versus things that we cannot simplify. So the first step I would take is to actually split this into 2 radicals. So all the things I can simplify over here, so all the things I can't over there. So that's step 1. Now, what I'm going to do is I'm going to break them into products, just like before. So 20, what are the products here? The 4 and the 5. The 4 goes here, the 5 goes there, because I can simplify this, I can't simplify that. So I break it into 4 and 5, and separate them. Simplifying guys, I'm going to put in the first one. Non-simplifying guys, I'm going to put in the second one. What about a cubed? A squared and a, right? Because this is an a to the 1, 2 doesn't divide into 1. I want numbers that the radical 2 can divide into. The b squared, well, the whole thing goes over here. What about the c cubed? Well, split into c squared times c. Right? So now I've separated the guys that I can divide 2's into the powers and the guys that I can't. Similarly, I'm going to go over here, the 45. 9 goes here, 5 goes here, because that's 9 times 5. A to the 5th. A to the 4th, and a to the 1. Right? Now, I could technically have done a squared and a cubed, but you notice that this can simplify further, right? You could break that down again into an a squared and an a. So you just break it down into the largest possible thing that's even to begin with. So you separate an a to the 4th and leave the a to the 1. And as for the c, this is c to the 1. That can't simplify, so I'm going to put it over here. So now, what do we have? We have 7a. This is going to be 2 times a times b times c. And I'm left over with radical of 5ac. Plus, here I have 5bc. This is going to simplify to 3a squared. And then I'm going to be left over with 5ac. So this is going to be 14a squared bc, radical of 5ac, plus 15a squared bc times the radical of 5ac. Right? So it breaks down to that. And now you notice the same pattern. The radicals, these are actually common terms now. So it's like I have this many apples plus that many apples. So I have 4, or even you can even take this. This entire thing is actually all the same. So I have 14 apples plus 15 apples, and I have 29 apples. So this all simplifies to 29a squared bc radical 5ac. And that would be the answer. So trick you can do with radicals, and again, we're taking advantage of the rules. I can split one big radical into two radicals, where, for convenience, put all the things I can simplify into the first one, put all the things I can't simplify into the second one. Simplify means the number that's on the radical can divide into the power of the thing. Yeah.
Why would it be 2a squared 2b 2c? Because you're adding them together.
Oh, because the radical of the a squared
No, on
cancels.
the bottom. Like, why would it be 2a squared 2b 2c?
Oh, because that's not a rule. What you're thinking of is the distributive law. If you are multiplying and across an addition, each thing gets a number.
No, I'm saying because you add the two terms together.
I didn't add it in.
Like 14 plus 15 is 29, then why wouldn't you do a squared plus a squared is 2a squared?
Oh, but we'll talk about that, but that's not the rule. Because if I had like 2x plus 3x, the answer is 5x's, right? Like I don't add an extra x and x. Right? Like I just multiply them to get this, and now adding them, I just worry about adding the coefficients. The tails will always stay the same, just copy it back down. I think there's a mix up with the distributive law there, we'll talk about that. We will talk about that.